Ferrous metals vary in their properties depending on the carbon content. This section briefly explains the metallurgical logic of iron carbon phase diagram. This is an illustration including essences of the iron carbon phase diagram. As I mentioned before, I believe that it is not necessary in machine design to understand the details of phase diagram. However, the essences of iron carbon phase diagram introduced here will give you advantages in understanding standards and heat treatment of various ferrous metals in your future. In the field of mechanical engineering, you may not be familiar with diagrams like iron carbon phase diagram. So, I would like to explain what this iron carbon phase diagram means in a simple way. Before thinking about the ferrous metals, we argue the states of water. You know that when ice, which is the solid state of water, is heated, it changes into water or liquid. And if it is kept heated up, it changes into gas, water vapor. Like water, ferrous metals also change their state when heated. You know that ferrous metals also change into a liquid when heated to extremely higher temperatures. However, in the case of ferrous metals, the arrangement of atoms changes before they become liquid, and the properties of ferrous metals vary greatly depending on the amount of carbon content. At room temperature, iron atoms are arranged in a body-centered cubic lattice. This state is called ferrite. At higher temperatures, the arrangement of iron atoms changes to face-centered cubic lattice. This state is called austenite. You have probably seen heated iron glowing red. That is the austenite. Water changes from solid to liquid at 0 degree, and at 100 degree, it changes from liquid to gas. Similarly, iron essentially changes from ferrite to austenite at 723 degrees, and at temperatures that are higher than 1000 degrees, it changes into liquid. However, the temperature at which it changes to a liquid or melting point depends on its carbon content. We are observing the details of these changes with respect to the phase diagram. Ferrous metals, regardless of the amount of carbon, is composed primarily of ferrite and cementite up to 723 degrees. Ferrite is relatively soft or ductile in nature. As mentioned before, ferrite has body-centered cubic lattice. Since the body-centered cubic lattice has small gaps, it accommodates few carbon atoms, which are contained in the ferrous metals within the lattice. Atoms that stay in crystalline structure is called solid solution. So, ferrite can accommodate very few carbon atoms as solid solution. The carbon atoms kicked out from ferrite crystals bond with iron atoms to form cementite. Cementite is known as a very hard and brittle material. Above 723 degrees, ferrite starts to change into austenite. Austenite is a crystal of face-centered cubic lattice. The face-centered cubic lattice has more gaps than the body-centered cubic lattice of ferrite. So, austenite can accommodate more carbon atoms as solid solution in a crystal than ferrite. At room temperature, ferrite dissolves only 0.008 to 0.02% of carbon, while austenite dissolves 2.1% of carbon. When ferrous metals of lower carbon content are heated up to higher temperatures, all the carbon atoms exist as solid solution in the crystal. So, the ferrite and cementite change into the structure that includes only austenite. As the carbon content increases, carbon atoms that are not accommodated in austenite bond with iron atoms to form cementite. So, when a ferrous metal of higher carbon content heated above 723 degrees, the crystalline structure is composed by both austenite and cementite. In order to understand the properties of ferrous metals, you need to be familiar with the crystalline structure composed of ferrite and cementite at room temperature. In iron-carbon phase diagram, the point where the carbon content is 0.8% and the temperature is 723 degrees is called eutectic point. At the eutectic point, ferrite and cementite start to form layered structure. This layered structure of ferrite and cementite is called pearlite. At the eutectic point, where the carbon content is 0.8%, the crystalline structure appears as only pearlite. In the region where the carbon content is less than 0.8%, the crystalline structure includes pearlite and ferrite. In the region where the carbon content is greater than 0.8%, the crystalline structure includes pearlite and cementite. 2.1% is the maximum carbon content accommodated in austenite crystalline structure. When the carbon content exceeds 2.1%, the extra carbon atoms are not accommodated in austenite, but exist on its own as graphite. So, the crystalline structure in this region includes pearlite, cementite, and graphite. Ferrous metals with higher carbon content is basically harder and stronger. This characteristic is due to the percentage of cementite, which is hard and brittle. The values 0.02%, 0.3%, 2.1%, and 6.7% are important carbon contents in ferrous metals. 0.02% is the maximum carbon content accommodated in ferrite crystalline structure. The ferrous metals with carbon content of 0.02 to 0.3% is called mild steel, The ferrous metals with carbon content of 0.3 to 2.1% is called hard steel. The ferrous metal with carbon content of over 2.1% is called cast iron. When the carbon content exceeds 6.7%, the crystalline structure is composed by hard and brittle cementite and graphite. In this state, the material collapses under its own weight, so it cannot be used for machine structure. You may remember these values and properties associating with the crystalline structure of ferrous metals.